Okay, good morning to all. I am going to start the class. Today I will close the chapter Work, Energy and Power from so many days onwards. I am going to start from so many days onwards. We are discussing the work, energy and power. Today is the last topic. If you have any problem and you can give in the comment. Now I am going to start the class and I will read the comment and by that I will give the reply for you. And then let us start. Good morning to all. Right. Our topic is conservation of energy in case of loaded spring. This is my topic, and this topic I am going to explain now. Conservation of energy means what? The total energy is remains constant. Whether the total energy is remains constant or not in case of loaded spring that we are going to discuss. Right, for that purpose, let us see here very carefully. If you have the doubt, you can write in the comment box while teaching if you will get the doubt. And this is the rigid support from that we are suspending one spring it here. And now this is the one load we are hanging at the end of the spring. And now this is the original position, and this position is called as the main position. Okay, this is at this position the displacement is zero. It is the original position. Just now let us what we do here, we pulled this loaded spring in the downward and release it. When you pull down and release it, it will start the oscillations. And now it takes some displacement at here. This displacement we can consider as x, and the displacement will is equal to plus a. We can consider it is an amplitude. What is a here? A is the amplitude, and this position is called as the mean position, and this position is called as the extreme position. Extreme position. And when you release from here, after pulling down, if you release from this location, okay, where this is the original location of the loaded spring, and you pull down and release it, and it starts the oscillations. Okay, it will start the oscillations, and then it goes up to here in the upward, right? And this is the higher position. And now at this position the distance traveled is a, and now this position the displacement is equal to plus minus a. What happening it here, it is doing the oscillations, it is moving up and down, right, along this path. Okay, it will do the oscillations like this. It goes up and down like this, it will do the oscillations, right? And during this its energy is remains constant. This is the location x is equal to 0 location is said to be mean position. Okay, and this is the main position, and this is also extreme position, and this is also extreme position. Extreme position means it has the maximum displacement at that location. It has maximum displacement at that location. Students, is it clearly appearing or not? Give in the comment box. Now let us see here. This location is called as the main position, and this location is called as the main position, and this one is the extreme position. This is also extreme position. It will do the oscillations like this. Now at the main position, it has the, you see the diagram and the cursor is moving in the diagram, and here this is the main position, and at here it started the moving. It has the maximum velocity, and it goes like this, and after coming to this position, its velocity becomes zero, and but it has large extension at here, right? And then it has the potential energy at here. What is the formula for the potential energy and kinetic energy? This loaded spring is oscillating. It has two types of energies. One is potential energy and other one is kinetic energy. Previously we derived the formula for the potential energy, that is half kx square. X is the displacement or the extension of the spring. K is the spring constant, and the potential energy in the loaded spring is half kx square. Let us start. Loaded spring. Loaded spring means some load we are hanging, obeys law of conservation of energy. Law of conservation of energy means its total energy is remains constant. Okay, total energy is remains constant. How total energy is constant? And from that, what equations you will get? If you go for mean position, right? Conservation of energy means energy conserved. Conserved means constant. The total energy is constant. What type of energies it has? One is the potential energy and other one is the kinetic energy. If you go for at mean position, okay, at mean position, what type of energies it has? At mean position, it has kinetic energy. Okay, maximum kinetic energy it has, because this is the mean position. From here, it should go up to here. That's why it should have, okay, it should have maximum kinetic energy at here. You see here, this is the original location. This is the x is equal to 0. This is the mean position. At mean position, it has a large kinetic energy. Then only it will goes. It has a maximum velocity, right? And then it will goes with that velocity this side, and then here it will become velocity 0. And this position is called as the extreme position. But it takes some displacement, and it here it has the potential energy, and that is half kx square. But the kinetic energy becomes 0 at here. But due to the spring force or the restoring force, it will try to bring the body to its original position. It will go back, but it will not comes to rest at here. Further it will goes to here, and then it will do the oscillations. It will goes up and down along this path. Okay, at the main position displacement is 0, because main position is the original position. From this, at this position displacement we can take as 0, no displacement. But when it is goes down, it takes some displacement, or when it goes up, it takes some displacement. That means displacement measured from mean position. Remember that. Displacement or the extension or the compression of the spring measured from measured from mean position. Remember it. Measured from mean position. Now let us see. At the main position, what energies it have? What is the potential energy? At the main position, displacement is 0. No extension, right? This is the original position. No extension, no compression. Okay, remember it. Okay, no change in the length of the spring. Then x is equal to 0 means potential energy. What happens? Potential energy of the spring formula is half kx square. Okay, x is 0 at here. That's why it does not have the potential energy. It has only what? Kinetic energy. Then the kinetic energy of spring, that is the kinetic energy, is equal to half mv square. M is the mass of the loaded spring, but it has maximum velocity. That's why this is the kinetic energy. Kinetic energy become maximum. Kinetic energy become maximum. Vm is what? Vm is the maximum velocity or the velocity of loaded spring at the main position. Okay, and now maximum velocity at main position. What is M? M is the mass of the load which is oscillating. It is going up and down. It is going up and down means we say that it is oscillating. It is oscillating. Okay. And now the total energy is what at here? The total energy is the sum of potential energy and kinetic energy. That is the total energy is equal. We will get as potential energy plus kinetic energy U plus K. We write that we will get as U0 because no extension at the mean position. At the main position not have any extension, that's why this is the total energy. And next at extreme position, if you will go at extreme position, what happens, what type of energies it has. Okay, if you have any doubt, you can write in the comment box. At extreme position, at extreme position, what type of energies it has. Extreme position means what? Okay, and we can also say it like this. Oh, what is this? I will write here, this is the extreme position. Okay, and this is the main position, and this is also extreme position. And now at extreme position, velocity becomes zero. Okay, look at here. It started from here with some velocity. It is going down, and when it comes to this location, right? You see the diagram, and it started from here with maximum velocity. When it comes to here, velocity becomes zero. Then it started further. It will not goes down. It will goes up, goes back. Then here it will become velocity maximum. Then again goes up, velocity decrease, and it will become zero at here. And after that it cannot go up further upward, it will go back. Then while going back towards the mean position, its velocity again increases. Then like this it will do the oscillations, right? While going from mean position to extreme position, this position to this position, mean to extreme, mean to extreme, what happens? Velocity decreases, kinetic energy decreases. At extreme position, displacement become maximum, displacement become maximum, that is plus a or the minus a. This is called as maximum displacement, is called as the amplitude. Okay, it is called as the maximum displacement or the maximum extension of spring. It is the maximum displacement or the maximum extension. Okay, maximum displacement. And now let us see what happens to the kinetic energy. The kinetic energy formula is half mv square. The velocity becomes zero at here. Okay, at extreme position velocity is zero. At extreme position velocity is zero and displacement maximum. Then velocity zero, if you substitute, then the kinetic energy you will get as the zero, means it is the minimum. Okay, at mean you see here, at the mean position potential energy minimum, kinetic energy maximum. But at extreme position, kinetic energy minimum, but the potential energy maximum. Why potential energy is maximum? Because x is equal to a, we have to write. That is, a is the maximum displacement. That's why it will become maximum. What happens to the total energy at here? What happens to the total energy? You take the screenshot and note it, and then I will continue it here. I'm going to erase. Is it clear, students? Any doubt? Okay, now let us see. We will find the total energy at here. Then the total energy at extreme position I want. Total energy at extreme position. What is the total energy at extreme position? Total energy means we have to add the two energies, right? That is the potential energy plus kinetic energy. Then what is the potential energy? Can anyone tell what is the potential energy? What is the potential energy? Potential energy is 0. Potential energy we write is 0 or maximum. It is the maximum. That is half k a square. And the kinetic energy is 0. Kinetic energy is 0. Why? Because velocity is 0 at extreme position. Then we got the total energy as half k a square. Right? This is the total energy at extreme position. Okay. From equation 1 and 2. From equation 1 and 2. Equation 1 and equation 2, you see total energy at mean position. Total energy at mean position is equal to total energy at extreme position. Because the law of conservation of energy is obeyed in case of loaded spring, that's why total energy should be equal. Then at mean position, you got the total energy as half mvm square. Okay, and total energy at extreme position is total energy at extreme position is half k a square. These two are equal. Now let us see at any position. For example, I want the total velocity at any position I want. I will apply the law of conservation of energy at any position. At any position I want to find the total energy. And then for example, this is the loaded spring, and this is the spring. It is the original position at here. This is the mean position. This is the mean position. At the mean position, the displacement is 0, and now it is pulled down, and then this is it takes some displacement at here. This is the displacement x, and now at this position, okay, at this position, displacement is x at here. Okay, it is the mean position, and here the displacement is x. Okay, we pull down at this position. This is not extreme position. This is not mean position. Okay, this is for example extreme position. Okay, no need of extreme position. We no need to draw here. And now at any position it has a velocity also, and the velocity is here. The velocity is considered as v. Okay, and at any position, total energy I want. For the potential energy we write is half k x square. Okay, because at any position displacement is x, and kinetic energy we write is half mv square. Then we write total energy. Total energy is equal to we write is half k x square plus half mv square we write. Actually, what happens at the mean position it has only kinetic energy. At the extreme position it has only potential energy. But in middle of the mean and extreme position, it has the potential energy and kinetic energy. Then we have to add this total energy. But total energy from equation 2 we write like this. But from equation 2, the total energy we write is half k a square, that is equal to half k x square plus half mv square we will get here. Here half is common and cancelled. Then we will get k a square is equal to kx square plus mv square. How you got this equation? This equation we got here total energy we wrote as half k square. This is from equation 2. This is from equation 2. And then we have to find out the mv square is equal to ka square minus kx square we will get. And mv square is equal we will get is k of a square minus x square we will get. Then I want from this v is equal to v square is equal to k by m of a square minus x square we will get. Then v is equal formula we will get is under root k by m into a square minus x square. Okay, right. And this is the formula for the velocity at any position. Velocity at any displacement x. Okay, at a displacement x, we can find out the velocity, and this we can consider as equation 4. Okay, right. And this is what is v here. Okay, what is v here? I will explain this based on the loaded what we derived today actually. And firstly, we derived about one thing, that law of conservation of energy in case of oscillations of loaded spring. Law of conservation of energy means what? Total energy should be constant. Then total energy is all constant for the loaded spring. That means at the main position we find out the total energy. At the extreme position we find out the total energy. And both we equate because according to law of conservation of energy, total energy should be equal. Then after that what we did, at any position, at any position, at the main position it has only kinetic energy. At extreme position it has only potential energy. And but in the middle of the mean and extreme position it has both energies, potential and kinetic energy. Right? Okay. Till now, if you have any doubt, you can ask. Is it clear? You can do in the chat box. Okay. I'm going to erase. If you have any doubt, you can test in the type in the box. Okay. Now I am going to rub this. It's not erasing. Okay. Now I am going to continue the last topic. More 10 minutes required. I will complete within short period, and everybody listen very carefully. And the topic is very important, very interesting also. And you listen very carefully. And this is the last topic in the work energy and power. Tomorrow I will start the new chapter. Okay. Right, the topic is vertical circular motion. Vertical circular motion. This is our topic. Okay. And now vertical circular motion. This is the last topic in the chapter. You see here, what is vertical circular motion? This is a circle, and now this is, we are taking one thread and we are connecting to some load at here. This load mass is m, and this free end is in our hand. Free end is in our hand, and now it is rotating. Okay, free end is in our hand, and now it is rotating like this. Now at the lowest point, the velocity is considered as the v1. What we are doing it here, we are taking one thread and some load we are hanging it here, and now this, just you do like this. For example, this is a nail. For the nail we are suspending one object, and now after this what you have to do, this is a nail, for the wall it is a nail. Okay, we are suspending one object by using thread. You throw this with some velocity, then it will do the vertical circular motion like this. It will do the vertical circular motion, it will go. You should give some minimum velocity to rotate along this circle, right? Here we are fixing at this point, and I am throwing this at here, then to maintain the object in the circular path. Okay, this is the fixed point. And thread is connected at here, one load we are hanging it here. Now you push this load with some velocity, then it will continue in the circular motion, and there should be some minimum velocity at the lowest point. This is the lowest point, and this is the highest point. There should be some minimum velocity to maintain this circle. If you throw from here, to maintain along the circle, there should be some minimum velocity. Less than that velocity if you will give, it will go up to here and come back. And to maintain complete circular path, there should be some minimum velocity at the lowest point. There should be some minimum velocity at the highest point. That minimum velocity is formula I am going to derive. You listen very carefully. Yes. Here, what are the forces which are acting? Here, the weight will act in downward direction. The tension will act in the upward direction. Tension in the string T1. And when it will come to some position, that at this position it came, and at this position it rotated by an angle theta. At this position also, the weight of the object will act in downward direction, and then to resolve this, we can do the extension like this, and this angle is again theta. We resolve the mg into components, right? One component, this is called as mg cos theta, and other component will be mg sin theta. Mg sin theta will be this side will be. And now this is the highest point. It came to highest point. For example, this is the location at the highest point. This is the lowest point, and this is the highest point. At the highest point, we can take its velocity as v2. Its velocity is v2, and here the tension is t2, and here the weight act in downward direction, that is mg. Okay. Now let us see some formulas I am going to derive. At lowest point, what we know? At lowest point, at lowest point, what are the forces acting on the object? Okay, at the lowest point, the forces acting is, one is tension that acting in upward direction. Okay, the tension is always acts towards the center. Tension is what? For example, you are suspending one object like this. This weight is acting downward direction, but even though it is not going down, means this string applies some upward force and protects the object from falling down. And this, the force generated in the string which protects the object from falling, is called as the tension. In this case, if it is at rest, then the tension must be equal to mg. This is the T is called as the tension in the string. T is called as the tension in the string. Let us see here at the lowest point what we know. At the lowest point, net force is what? Net force. Net force, downward force is mg. Downward force is mg at the lowest point. Upward force is T1. The net force is T1 minus mg. Why T1 minus mg? Because here T1 is more because it is going up like this. Then T1 minus mg we write. But net force, this net force serves as centripetal force. But because it is moving in the circular path to maintain any body in the circular path, centripetal force is required. This net force serves as centripetal force. Then we write centripetal force formula it here. That is mv1 square by r, where r is the radius of the circle. That is equal to length of the string. Okay, mv1 square by r is equal to, we write as T1 minus mg. Okay, and from this tension at the lowest point, if you want, then we will get as mg plus mv1 square by r. Okay, this is equation 1. What is this here? T1 is the tension at the lowest point. Tension in spring at lowest point. At a lowest point. And V1 is what? Speed of object at the lowest point. Now, here we got T1. At the highest point also I want to find out the tension. At the highest point. At highest point, what is the tension? At the highest point tension, if you want, then you have to find out the net force. Okay. Then you know T2 is the tension at the highest point. The net force formula we write is, you see the diagram, and the at the highest point, this is the highest point. At this point, tension is downward. Tension is always towards fixed point because the center point is the fixed point. This center point is the fixed point. Tension is always acts towards the fixed point. The net force tension is T2 at the highest point, and weight also acting towards downward. Then total force is T2 plus mg. But the net force acts as a centripetal force. But the centripetal force formula is mv square by r. But at the highest point, the velocity is v2. That's why we write as v2 mv2 square by r plus T2 plus mg. Right? And now from this, if you want to find out the T2 we write as mv2 square by r minus mg we write. This is equation 2, and T2 is the tension at the highest point. T2 is the tension at the highest point. Tension at the highest point. And V2 is the velocity at the highest point. And now I want the difference. Okay. And for example, if you want to find out the difference between these two tensions, equation 1 minus equation 2 I want. If you want to find out the difference in tensions, then left sides you subtract and right sides also you subtract. When you will subtract right side, you will get T1 minus T2 is equal to mg plus mv1 square by r plus, sorry, subtraction we want to do. When you will do the subtraction, then it will be minus, then minus mv2 square by r plus mg you will get. What I'm doing it here, equation minus equation 2, equation 1 minus equation 2, both we have to subtract. Left sides you have to subtract and right sides you have to subtract. Okay, then you will get this equation, and after that we have to simplify this, and for the purpose here we have to erase it, and more 5 minutes required to close the class. This is not working. Okay, manually I will erase. Okay, next continuation. Yes, what you have previously, what we derived, what we got it here in the last one. Difference we find out. Difference we got as T1 minus T2 is equal to T1 minus T2 is equal to we got as MV Mg plus Mg. We will get 2 Mg plus T1 minus T2 is equal to we will get on the right side 2 Mg plus M by R is common. Then we will get V1 square minus V2 square. This is equation 3. T1 equation 1, T2 equation 2, T1 minus T2 equation 3. Then we will apply the law of conservation of energy. According to law of conservation of energy. Law of conservation of energy. What you know law of conservation of energy? According to the law of conservation of energy, the total energy should be remains constant. Means total energy at mean position. Total energy at the lowest point is equal to total energy at the highest point. Right? Total energy at the lowest point is equal to total energy at the highest point. Right? What is the total energy at the lowest point? Total energy lowest point is mgh. Sorry, total energy at the lowest point. You see the figure. From the figure, we have to write the total energy. Then you let us draw the diagram it here. This is the circle. At the lowest point, we can take its height is 0 at here, and it has the velocity v1, and its height we will take as reference point. This height we can take as 0 at here. Okay, and this is the highest point here. The velocity is v2. It is going along the vertical circle. This is the radius r. And now at lowest point total energy I want. Potential energy is mgh. H is we can take 0. Okay, this we will take as a reference point. Lowest point we can take as the lowest reference point. From that only it is going up. We can take initial height is 0. At this location we can take as the height is 0. Okay, when it come to here, what is the height? Here this will be r and this will be r. Height become 2r at the highest point. At the lowest point, highest here is 0. This is the 0 height. It is not more to any height. Then when it is going like this, when it come to highest point, its height become 2r. Then at the lowest point, potential energy is 0, kinetic energy of mv1 square, and total energy at the highest point mgh. H is what? 2r. And kinetic, this is the potential energy mgh at the highest point. At the highest point, potential energy is there, h is there, and kinetic energy of mv2 square, because at the highest point velocity is v2 of mv2 square. Okay, this is the v2 is the velocity at the highest point. Now we substitute, we simplify this, and then we will get if you simplify this, we will get v1 square is equal to v2 square plus 4gr we will get. Okay, and if you find out the v1 square minus v2 square, then you will get as 4gr, and this equation is the 4, and equation 4 substituted in equation is substituted in equation 3. You will get the difference in tensions. Then what you will get? T1 minus T2 is equal, we will get as 2 mg plus m by r into v1 square minus v2 square is 4gr, and then this is cancelled. Then you will get as T1 minus T2 as 2 mg plus 4 mg. Then we will get as T1 minus T2 is equal to 6 mg. Okay, they may ask the question that show that the difference in tensions in the vertical circular motion is, okay, 6 mg. Okay, and then what is the minimum velocity at the highest point? At the highest point, at the highest point, tension should be greater than or equal to 0. This is the tension, minimum tension 0 hona chahiye, right? Minimum tension equal to 0, or otherwise it may be greater than this one, then it will maintain in the circular path. If this condition satisfied, then maintain in circular path without uh, stopping. Maintain in circular path. This is the condition to maintain in circular path. To maintain any body in the circular path, vertical circular path, okay, to maintain in circular motion, this is the condition, right? And the tension T2 is what from equation 1, or sorry, equation 2. Can you tell? That is what you got, equation 2, T2 plus mg is equal to mv2 square by r. That means tension T2 equal to mv2 square by r minus mg. This is T2 formula. You see the equation 2. From that equation 2, we wrote this one. Okay, that is from equation 2. And now, if you simplify this, we will get mv2 square by r greater than or equal to mg. And now mm gets cancelled, and then v2 square is equal, we will get as v2 square greater than rg, we will get, and v2 greater than or equal to 1 root rg. What is the minimum velocity at the highest point in order to maintain in the circular path? The minimum velocity at highest point, minimum velocity at highest point to maintain in circular path. सर्कुलर पाथ में चलाने के लिए कम से कम कितना वेलोसिटी होना चाहिए हाईएस्ट पॉइंट के पास, उससे फॉर एग्जांपल देखिए, इधर इधर कुछ वेलोसिटी होना चाहिए, नहीं डायग्राम देखिए एक बार, इसमें इधर कुछ वेलोसिटी होना चाहिए v2, इससे वेलोसिटी कम होते तो इधर से ऐसे नहीं जाएगा, इधर से ऐसे नीचे डायरेक्ट गिरेगा, मतलब वो कुछ some velocity is required to maintain any body in the circular path. That velocity is the v2. And what is the minimum velocity at the highest point? Highest point, highest point. The minimum velocity at the highest point is, you see, that is under root rg. This is the minimum velocity at the highest point. Then what is the minimum velocity at the lowest point? Minimum velocity at the lowest point is what? Minimum velocity at lowest point. Velocity may be greater than or equal to under root rg. Greater than or root, it may be more than root rg, or minimum it should be equal to root rg. There is a minimum velocity to maintain any body in the circular path. At the highest point is root rg, and at the lowest point is what? Then at lowest point, if I will tell, then this topic will be complete and chapter also completes. At lowest point, what is the formula to find out the velocity? Then you see from equation 4, right? From equation 4, we write v1 square minus v2 square is equal to 4gr, right? You substitute the v2 as root rg at here. Okay, then v1 square is, v2 is root rg. The minimum v2 value is root rg minimum. Okay, minimum v2 value is root rg. Then we write here root rg square, that is rg, is equal to 4rg. Then if you simplify this, we will get v1 is equal to under root 5gr. Direct step I wrote, note it. And this is the minimum velocity to maintain any body in the circular path. Okay, and this is considered as a circular path. Okay, and here we are fixing one. Here this is a nail, and we are hanging one object by using string, and then you push with some velocity at here, then it can go in the circular path, right? After going to some distance, it should not return back, it should move, it should not. Okay, you see here, this is a once again I am explaining, this is the center point, and we are hanging some load at here, and we are pushing with some velocity. There should be some minimum velocity at here required, then to maintain in the circular path. If you will do less velocity, it will go up to here and come back. But to maintain complete circle, there should be some minimum velocity. That is the minimum velocity at the lowest point is root 5gr, and minimum velocity at the highest point is root gr. To maintain any body in the circular path, there are the velocities. In the circus, you see in the circus, right? In the circus, you will see this is a, for example, circle road. One bike, they will move like this. They will move the bike. Okay, and this is a bike. The bike will go like this, like this, like this, or cycle, it will goes in the circus, right? And they will move along this like this. There should be some minimum velocity at here, there should be some minimum velocity at here. Otherwise he will fall down after going to certain height. For example, this is a circular curved road, a curved sphere, let us consider. Then vertical circle it is. Vertical circle means circle is standing just like y-axis. And then here bike started it. Then it should have some minimum velocity to maintain in the circle path, that clearly. Then that minimum velocity at the lowest point and minimum velocity at the highest point. Okay, the biker should go with certain velocity to maintain what complete vertical circle. Or otherwise, if you will go with less velocity, he will fall down like this. You see the diagram clearly. From here, if you will go less than certain minimum velocity, that is the minimum velocity at the highest point, that is root RG. If you will go less than this velocity, he will fall down through the air in the downward. Right? And this, thank you for watching lectures. Topic is complete.